Hello everyone. Today I would like to talk about my recent work on one-way functions and Kolmogorov complexity. This is a joint work with Professor Rafael from Cornell Tech. So first, let us summarize the history of cryptography in the last 2,000 years. And people have proposed many encryption schemes, which is amazing. However, none of them is really secure. And a story of the scheme begins with an artist who invents the scheme. And of course, no one can really prove that the scheme is secure. So people can only rely on the fact that the scheme is secure against ordinary attacks. And the scheme will be deployed and people will use it in their daily life. However, sooner or later, someone will break this scheme and people have to wait for another new scheme. And it seems that we have been going around this cycle for a really long time, and we can never prove that a scheme is secure. So we only want one scheme, a single scheme, in the sense that if this scheme is secure, then we have secure encryption scheme. And if this scheme is insecure, then there exists no secure encryption scheme, and we don't have to go into this cycle for one more round. And Diffie and Helmer in 1976 proposed a genius notion of one-way functions, which gives us a way out of the cycle and brings us into the age of enlightenment. So a function f is one way if it's easy to compute but hard to invert. Namely, if you have the string x, it's easy to compute f of x. And if you only have f of x, it's hard to get back to the inputs x. And an example of one function is based on the factoring problem. So in which we use the input x to pick two large random number p and a large random primes, p and q, and we output p times q. So if on input p times q, if we want to get back to the input x, we have to factor the large number, which is assumed to be hard. And let us take a look at the formal definition of one-way function. So function f is a polynomial time computable function, and is for every polynomial time algorithm a, the probability that on a random image of f, A finds a pre-image is at most some negligible amount. And the good news is that one-way functions are both necessary and sufficient for a bunch of crypto private key primitives, such as private key encryption, pseudorandom generators, digital signatures, authentication schemes, and so on. And although PKE, OT, and obfuscation are not included, so one-way function is basically the minimal assumption you can make if you want to obtain a secure encryption scheme. So whether one-way function exists is the most important problem in cryptography. And let us take a look at what does it mean by the existence of one-way function. And a simple observation is that the existence of one-way function implies NP is not equal to P. And our holy grail proposed by Diffie and Helmer in 1976 is to show that NP is not equal to P implies the existence of a one-way function. So if this is true, we can base the existence of one-way function on really a relatively weaker assumption, that is NP is not equal to P. So if NP is not equal to P and we get one-way function for free, and if there exists no one-way function, then we know NP equals to P and the power of polynomial time algorithm is beyond our imagination. However, this is a still very hard problem, and there are a lot of partial black box separations between NP is worst case hard and the existence of one-way functions. In the absence of the holy grail, people have also proposed a lot of one-way function candidates based on a different assumption, such as the hardness of factoring problem, the hardness of discrete logarithm problem, and the hardness of lattice problems more recently. In addition, people also believe that those encryption schemes used in practical, such as DES, SHA, AES, are secure. So far, those primitives have not been broken, but the question is for how long? So all those primitives, the famous Vigenère encryption scheme had been secure for 400 years. And in 400 years, no one can break it. However, nowadays, breaking it is as easy as the first homework in your crypto class. So cryptographers seldom sleep well, said Mikhaili in 88. And although we have the beautiful notion of one-way functions, it seems that we keep proposing new candidates. And we know that if we have quantum computers, actually the two candidates, factoring problem and discrete logarithm problems, are actually easy and can be solved by a quantum computer in polynomial time. So the question is, have we really escaped from the crypto cycle? And we really want to have a single computational problem, in the sense that if this problem is hard, then we have one-way functions. And if this problem is easy, then there exists no one-way functions. And so the central question is, does there exist some natural average case hard problem that characterize the existence of one-way functions? And fortunately, the answer to this question is yes. And our main theorem says one-way functions exist if and only if t-time-bounded Kolmogorov capacity is mildly hard on average. So let us introduce the notion of Kolmogorov capacity and consider following two strings. The first one is 1, 2, 3, 1, 2, 3, 1, 2, 3, and so on. And the second one is 1, 7, 3, 0, 5, 4, and something, something. So the question is, which of the above strings is more random? And the notion of Kolmogorov capacity is used to measure the amount of randomness in a fixed string. So the Kolmogorov capacity of X, denoted by K of X, is defined as the length of the shortest program that outputs the string X. And more formally, we fix a universal Turing machine U, and we are looking for the length of the shortest program pi, which consists of M and W, where M is the description of a Turing machine and W is the string on its input tape, such that the universal Turing machine U, when simulated on machine M, will output the string X. And the notion of Kolmogorov capacity has a lot of amazing applications, such as proving Gödel's incompleteness theorem, but unfortunately, it is uncomputable. So let us consider the notion of time-bounded Kolmogorov capacity. So a k subscript t of x is defined as the length of the shortest program that outputs x within a time bound, namely a t of the length of x. So obviously kt of x is actually computable by enumerating all the possible machine and running every machine in a fixed running time. However, the question is, can kt be efficiently computed when t is a polynomial? And this problem has been studied in the Soviet Union since the 60s, and also independently by Hartmanis, Sipser, and Co. in the 80s. And it is closely related to the MCSP, namely minimal circuit size problem. And let us introduce the average case hardness of KT. So actually, this problem has been studied even before the establishment of the theorem of average case hardness. And in the 60s, in the Soviet Union, they call it a frequential version of computing KT. And they were asking, does there exist an algorithm that computes KT of X for a large fraction of X? And a simple observation, also made in the 60s, is that kt can actually be approximated within an additive factor of d log n with probability 1 minus 1 over n to the d. So with very high probability. And the approximation algorithm is so simple, and you only have to output n, where n is the length of the input string. And to see why this is a good approximation, just consider like the number of a Turing machine with description length at most a n minus d of d log n is at most 2 to the n minus d log n. And so they are really sparse amongst the string, the universe of string of a length n, where there are 2 to the n different strings. So the simple algorithm approximates the KT complexity of a random string with a very high probability. And let us introduce the notion of mildly hard on average. So we say KT is mildly hard on average if there exists a polynomial P such that no polynomial time heuristic H can compute KT with probability 1 minus 1 over n, 1 over P of n over random string X and infinitely many n. And we can also define KT is mildly hard on average to C approximate in the same way. So our main theorem says the following are equivalent. First, one-way functions exist. Second, KT is mildly hard on average. And third, KT is mildly hard on average to C log n approximate. And we will have the following simple corollaries from our main theorems. And today, because we don't have enough time, we will just sketch the proof from KT is mildly hard on average to the existence of one-way functions. And we refer you to the full proof of the main theorem to our paper. So today we'll see the proof of theorem 1, which is assume KT is mildly hard on average, then one-way functions exist. So to show that one-way functions exist, we only have to show weak one-way functions exist. And it is a function f such that no polynomial time algorithm can inverse f with probability 1 minus 1 over P of n for infinitely many n and some polynomial Pn. And by the hardness amplification lemma for one-way functions, if a weak one-way function exists, then a strong one-way function exists. So we only just need to construct a weak one-way function. So let us take a look at our constructions. Let C be a constant such that KT of x is smaller than the length of x plus c for all string x. And to see this is true, consider for any string x, the Turing machine with the string x hardwired in the description, and the rest of the machine is just outputting whatever is hardwired. So we take a length of x bits to hardwire the string x, and we take another c bits to write a machine outputs whatever it's hardwired. So there exists a Turing machine of length of x plus c that outputs x. So the KT complexity of x is at most the length of x plus c. And our function f on input pi prime comma I, where pi prime is a n plus c bit string and I is a log n plus c bit string. So f first truncates pi prime to the first I bits and denote the truncation, so by pi. And f interprets this string pi as a program, and f runs it for t of n steps, and let y denote the output of pi. So in the end, our function f outputs I concatenated with y. And we claim that this function f is a weak one-way function. So assume for contradiction that f is not a weak one-way function, Then for every inverse polynomial delta, there exists a polynomial time attacker A that inverts this function f with probability 1 minus delta. And we construct a heuristic h using this one function inverter A that computes kt with probably 1 minus delta times of n, which conclude that kt is not mildly hard on average, and we reach a contradiction. And then let us introduce how we construct this heuristic h by using this inverter A. And our heuristic h on input of a string of length n, h tries all possible I from 1 to n plus c, and h runs the inverter A on input I concatenated with y. So recall that if this inverter succeeds, it would return a Turing machine of description length I, such that this machine produces the string y. And let us denote the machine by pi. And note that this inverter can also fail. So we have to check that if pi outputs the string y within t of n steps. And finally, the heuristic outputs the smallest I for which the check passed. And intuitively, if A succeeds with very high probability, and then it should also succeed with very high probability when conditioned on length I for every I in n plus c. However, our one-way function inverter A is only guaranteed to work when input is a uniform random image of the function f, and the problem is here h is feeding A the round distribution over y's. And let us take a look at those two different distributions. So in the one-way function experiment, where A is guaranteed to work, I is basically a uniform number from 1 to n plus c, and the string y is the output of a random program of length I. And in this KT experiment, where we want to show that A works, I is basically a fixed string, and I is set to be the KT complexity of y, and y is a uniform random string. So we have no reason to believe that the outputs of a random program will be close to a uniform distribution. However, using a counting argument, we can actually show that they are not too far in relative distance. So our key idea is as follows. We first assume that for simplicity, A is a deterministic algorithm, and we consider some string y on which our heuristic fails. So consider in this case a experiment, a string y will be sampled with probability 2 to the minus n. And for h of y to fail, our one-way function inverter A must fail on input w concatenated with y, where w is the KT complexity of y. So if the KT complexity of y is w, then we know that there exists a Turing machine with length w that outputs y. So if X succeeds, A must find this Turing machine, and our heuristic will be correct. So A must fail on this input. And the pair W concatenated with Y is sampled in this one-way function experiment with probability at least 1 over n plus c times 2 to the minus w. To see this, so basically with probability 1 over n plus c, a uniform I will hit a w, and with probability 2 to the minus w, a random program will hit the program that produces y. So, and we can further show that this probability is at least 1 over n times n to the times 2 to the minus n. So if h fails with probability epsilon, then A must fail with probability at least epsilon times of n, which by our choices of parameters is at least delta. Thus, h fails with probability at most delta times of n, And we show that H is a good heuristic to compute KT, which is a contradiction. So we conclude that our function f is actually weak one way, and we get a one-way function. And so now we have seen that one-way functions imply KT is mildly hard on average implies the existence of one-way functions. And in our full paper, we'll prove that the existence of one-way function will also imply KT is mildly hard on average. So to conclude, our main theorem is one-way functions exist if and only if KT is mildly hard on average. So this is the first natural average case problem that characterizes the feasibility of the basic task in crypto, such as private key encryption, digital signatures, pseudorandom generators, and so on. And finally, let us record some recent results on KT and friends. So Hilala 18 shows a worst case to average case reduction for KT. Namely, KT is errorless hard on average if KT is worst case hard to approximate. However, our results do not extend to errorless hard on average. And Ilango, Love, and Olivia 20 shows that multi-MCSP is MP hard. And Olivia and Santharnan shows the hardness implication for MCSP, the minimal circuit size problem. And finally, let us end this talk by summarizing our progress towards the Holy Grail. So our start point is that assume NP is not equal to P. And we know that multi-MCSP is also hard for BPP. And if we can show that it implies K-poly is hard to approximate for BPP, and by Hilala 18, we can show that K-poly is errorless hard on average. And if we can show it implies K-poly is mildly hard on average, and by what we have seen today, we know that one-way functions exist. So the red dashed arrows are the mission implications, and we believe that we are getting closer to our Holy Grail. So thank you for listening.